Okay, here we go, students. I regret to inform you that you will not be seeing my face this time. You'll only be hearing my voice and seeing me write on this iPad screen, which is actually your computer screen. But anyway, yesterday we were talking about this whole situation here with a force probe, you know, that thing right there with the special elastic bands from NASA and the paper clip. I mean the what did I call that? The special retainer clip. So this was useful for the following reason. Here's the deal. The hand was exerting a force on the faucet. That force was in this direction, and the force of the faucet was acting in this direction. But I had no way of showing that until I got out the force probe. And so the force probe showed that it didn't matter what I did or how I pulled on my side of the force probe, each of these rubber bands were going to stretch the same amount. In other words, there's no way I could have pulled in a way that would make this rubber band a different length than this one. Meaning that what my hand is doing to the faucet is what the faucet is doing to my hand. So let's think about force diagrams and what those look like here. So if I'm drawing a force diagram for my hand, and let's just, for the moment, let's just forget about gravity. It's just going to complicate things here. So if this is my hand here, and I'm going to draw a force diagram for my hand, here's another stipulation we have to provide here. I'm pretending that this isn't there. Okay? The only reason that the force probe is there is for you to see that I can't stretch these different lengths. So the actual scenario we're going to draw force diagrams for are for when my hand was actually in contact with the faucet, not with the force probe there. That's only there to show you the size of the forces being acted or being enacted. All right, so here we go. Back to the force diagram. My hand is pulling this way, or excuse me, I take that back. My hand is being pulled on in this way. By what? What is pulling? What's exerting a force on my hand this way? Oh, I don't know if you know this. It's my arm. So I'm going to say force of arm on hand. Now, some of you already got to this yesterday, and just deal with it. The rest of you, you'll get right now. So that's not farm on hand, it's force of arm on hand. Now, what's acting in the other direction? What's pulling this way on my hand? Well, yeah, the force probe. Well, remember, this is when I was actually touching the faucet. So I'm going to say the faucet is pulling this way. So the faucet's pulling this way. Force of faucet on hand. Oh, I tell you, this pen thing is terrible. It's a pen that has a stylus thing on the end, and oh my gosh, it's awful. So anyway, you get the point. Force of arm on hand this way, force of faucet on hand this way. How do you think those forces compare? Well, they're probably equal in amount, opposite direction, because my hand is not accelerating. Because my hand's not accelerating, that means the forces have to be balanced on my hand, and so we're going to say that those two forces are balanced. Now, how about the force diagram for the faucet? Well, let's do that here. What is acting this direction on the faucet? Well, you might say the force probe. Well, no, not the force probe. Remember, my hand was in contact with the faucet. So I'm going to say my hand is in contact with it. And so I'm going to draw an arrow like that. And I'm going to say that that is force of hand on faucet. Oh, and by the way, we're talking about, as you can see here, interactions between objects. When objects interact, what happens? Well, forces happen, okay? Forces happen when objects are in contact. So, or when they interact, I should say. They don't have to touch because remember the earth can exert a force and it doesn't touch necessarily. So, force of hand on faucet is pulling the faucet this way. What's pulling the faucet this way? Well, I guess the table. We'll say the lab table or the table. So we also have a force this way on the faucet, and it'd be force of table on faucet. Now I want you to look at these force diagrams. And again, we could say those are balanced as well because the faucet is not experiencing any acceleration. So we have two different force diagrams. This one's balanced, this one's balanced. And two of the forces I want you to pay close attention to here. We have a force here and we have a force here. Do you notice anything about the names? And again, some of you, I mentioned this yesterday. This name is a reciprocal, you could say, of this name. Force of faucet on hand, force of hand on faucet. So what exactly does that mean? Well, it is the interaction between the hand and the faucet and what they do to each other. Well, what do they do to each other? In other words, how does this force compare to this force? Well, the rubber bands tell us, right? My hand does this much to the faucet does this much to my hand. And how do they compare? Equal amounts. Notice the directions of the arrows. The force of the faucet on the hand is to the right. The force of the hand on the faucet is to the left. So the rubber bands tell us that those forces are the same amount. Our diagrams tell us they're in the, yes, opposite direction. And there's something else here. Are they in the same force diagram? No. This force on hand is in the hand's force diagram. This force on the faucet is in the faucet's force diagram. They are not in the same diagram. These are called a force pair. Okay? These are called a force pair. Incidentally, every force has a pair. Force pair. There are three things about force pairs. We just talked about them. Number one, they're equal in amount. So the size of the force is equal. Two, what do we know about the direction? They're opposite. You probably ought to be writing this down. So they are in the opposite direction. If you aren't writing it down already, if you haven't written any of this down, you should probably be writing this down. So equal size, opposite direction. I may want to finish that, direction. And lastly, they are in different, oh boy, I can't write or spell. Oh no, I don't think it's going to let me erase that. Oh my gosh, I don't even know what I'm writing right now. In different force diagrams. In other words, they're not acting on the same object. Look, it's on hand. This one's on faucet. They can't be in the same diagram. That means all of our conversations about balanced versus unbalanced that does not apply to force pairs. So that is not part of the conversation. There is no balance or unbalanced because they're not in the same diagram. They're not balancing each other out because they're not acting on the same object. I hope you're getting this. So these then are the three things that will tell you if you're dealing with a force pair. Okay, they're equal size, they're opposite direction, they are in different force diagrams. The names are dead giveaways. Okay, force of faucet on hand, force of hand on faucet. They are reciprocals. The names are opposites. Opposites. So let's take a look at a couple other things here. I think that's all I need to tell you on that slide. To this slide. This slide here. Wait a second. Yeah, that's the one. I guess that's the one. We have a block on a table. All right, block on the table. It's pretty obvious. Let's think about force diagrams here. And maybe we don't even need. Well, I guess we might need the ground. I don't know. Do we need the ground? Floor? I don't know. All right. So quickly, let's draw a force diagram. Maybe you should be doing this in your comic books as you watch. Trying to draw a force diagram ahead of me. You'll probably beat me anyway. So if the table force diagram is over here, let's just say we have force of, I don't know, force of gravity on table, right? I'm just going to shorthand T there because this pen doesn't work very well. So force of gravity on table. We also have force of floor, right? On table. What else do we have? Well, it looks like object A is acting on the table. So we'd have another force here. In what direction? Well, A is acting down on the table. So we might have force of A on table. And there it is. Right there. Now that means I probably should have made this a little bit longer because that's not going to be balanced. The three of those, oh boy, let's forget about that for a second. So object A over here. This book, let's call it a book, I guess. So the book on the table. The book is experiencing forces as well, and it experiences a gravity force. Yeah? Yes. Force of gravity on, what did I say? Book, yes, book. No, on A. Gosh, A. Let's just call it object A. It already has a name. A. Force of gravity on A. Now, what else is acting on A? Well, the table. Okay. So the table is acting in that direction on A. So we would say force of table on A. Now, wait a minute. Haven't we seen a force similar to this somewhere else? Oh, yeah. That force looks an awful lot like this force. Let's compare them, shall we? Oh, yes. So this one, force of table on A, is up. It's in A's force diagram. This one here is force of A on table. Okay, table on A on table. Oh, look at that. It's like they're reciprocals of each other. Notice, this one is in the downward direction. Oh, look at that. They're opposite. They are opposite directions. They're also in different force diagrams. Their names are dead giveaways. So now the question is, are they the same size? In other words, is A doing to the table the same or different than what the table is doing to A? I would say it's the same. A is doing to the table what the table is doing to A, but they're doing it in opposite directions. This is a force pair. Okay, this is a force pair. Forces always exist in pairs. Why haven't we seen a force pair yet? Why isn't it until now that we've even seen a force pair? Because we've never drawn force diagrams for two different objects at the same time. So when we had the dry ice on the table, if you remember back to that, were there force pairs involved? Yes, but we didn't have any drawn because we didn't care about the table. The chunk of dry ice was sitting on the table. Did we draw a force diagram for the table? No. We drew a force diagram for the block of ice, or like the book in this case. So we didn't care what was happening at the table because the book in this case, or the dry ice then, was our system. It's the one we cared about seeing what the forces were doing. So we haven't seen force pairs because, again, we haven't looked at more than one object at a time. We haven't looked at it when two different objects are interacting and then look at both objects in the force diagrams. So that's why we haven't seen them yet. So what about them? Well, it leads us to Newton's third law, and I hope you're writing this down. Newton's third law. Most of you, probably if I start saying it, you could finish saying it. Every action, some of you may have even started to say it yourself. Every action has, oh my gosh, I can't, an equal, what did we say about force pairs? They're equal and opposite reaction. Now, a lot of people know that law, but they don't really know what it means. Well, right now, I'm trying to explain to you what it means. All right? So we're saying that every action, every force has a force pair. It has an opposite force in a different diagram, equal in amount, opposite in direction. That's what the third law says. Moving on. Oh, look at this. Isn't that lovely? Isn't that a lovely sketch? So here we have a football player kicking a football. I know. The art is fantastic here. I mean, you should try to sketch this. Probably. You may have to pause the video. It's such a good drawing. It's going to take you forever to get this thing right. So I have a foot kicking a ball. Now, in the previous two situations, with the hand and faucet and the book and the table, were either of those two objects doing any moving? No. And we called it a force pair, right? They were acting on each other with equal amounts of force. So now the question becomes, okay, so how does the football player's foot, how does the foot acting on the ball compare to the ball acting on the foot? I hope you can see. If we were to name those forces, what would they be named? Well, we would have one that would be called force of ball on foot, and we would also have a force called force of foot on ball. Do you see the names here? How are the names? They're dead giveaways for a force pair. In other words, the foot is not doing any more or less to the ball than what the ball is doing to the foot. Well, then wait a minute. Why is the ball then going to have this huge acceleration as it goes off into the air, and the foot doesn't seem to have much of an acceleration, even though they're both experiencing the same amount of force? Well, think about it. How massive is the ball? That has a little tiny mass and a huge acceleration, right? The foot, which is connected to the leg, which is connected to the person's body, that's a big mass. How much acceleration is it going to have? Tiny. Okay, so I hope you're getting that, all right? Why does it look like the ball experiences more force than the foot? Because it's less massive and it's going to experience more acceleration when it experiences the same force as what the foot experiences from the ball. The foot seems less affected because it's more massive and its acceleration is smaller. Force pair, equal and opposite reaction. The foot is not pressing on the ball any more than the ball is pressing on the foot. Moving on. Oh boy. Another great one here. So pickup truck. Notice by the motion lines, the pickup truck is actually beginning to roll down the hill. It's accelerating down the hill. This poor guy here, oh my gosh, dripping with sweat, working his tail off. He cannot push the truck hard enough to keep it from rolling down. So, do we have a force pair here? Well, let's think about it. Oh, it looks like we're going to have, I don't know, force of truck on man. Sure. Are we going to have force of man on truck? Yes, because again, they are acting on each other. They are interacting. These two objects are interacting. And that produces a force pair. The question is, how do those forces compare in size? Well, what do we know about force pairs? They're equal in amount, opposite in direction, in different force diagrams. So, is this going to be in the same force diagram as this one? No, this is in the man's diagram. This one is in the truck's diagram. Not in the same diagram. How do they compare? They're the same amount, but in opposite directions. Do you see? Let's think about this. Which one has more mass, the man or the truck? Oh, definitely the truck. So the truck is pushing the man with the same force that the man is pushing the truck. What's making the truck roll down the hill? Well, obviously gravity. I mean, gravity's having an impact on this truck here. So the truck is rolling down the hill because of gravity. This poor guy doesn't have enough force to make it stop. It's way more massive than he is. So the force that he can exert, the force that he can exert on the truck, on that large mass of truck, is not going to stop it. But the force that the truck exerts on the man and his little mass is enough to make him slide on down the hill. Okay? There's still equal amounts of force, but they're acting on different objects that have different masses. And therefore, the effect of each of those forces looks different, even if the size of the force is the same. I hope that you're getting this. All right. So, sorry that was such a long video, but hey, you're welcome. There's an assignment you'll be working on as well that should be on Classroom. So enjoy the rest of your day. We'll see you tomorrow.